Alright, this is for Astronomy 101, the solar system. I'm going to go over the PowerPoints, and I can only record these, just to let you know, in 15-minute increments. So if it takes longer than that, there'll be like a, part 1, part 2, part 3, and so forth. Alright, so let's get started. So the first thing is as it says here, is charting the heavens. And so we have a nice picture that shows the Milky Way. There's a nice telescope as well, an observatory. Alright, so these are some of the things that we're going to talk about. Where we are in the universe, what it is, what makes something scientific. I guess I should point that out right now. The biggest thing in the last 400 years was the using experiments, the experimental method. So, the people had lots of ideas about how the universe worked, but about 400 years ago, the human race invented this idea of testing our ideas using experimentation, and that's true in all forms of science. For them to be for something to truly be scientific. All right, so we'll talk about the rest of this stuff, how the Earth moves, how the Moon moves, measuring distances, and using geometry, and of course we'll look at the study of the entire universe very briefly. Of course, this is mostly about the solar system, but we got to get a sense of where we are. So one thing to start off with is some units that we use to measure things. In astronomy, usually with the solar system, you talk about what's called an astronomical unit, an AU. And AUs are the distance between the Earth and the Sun, the average distance between the Earth and the Sun, because the distance varies, as we're going to talk about in a little bit. When we get to Kepler's laws. But anyhow, when we go further than our solar system, to the next star, for example, near the Sun, we have to talk in units called light years. Then that is, of course, the distance that it takes light to travel in 1 year. So if something is, 4 light years away, like the nearest star to us, it's a little more than 4 light years away, called Proxima Centauri. It's in the southern hemisphere. You can't really see it from here. Anyhow, you can't see Proxima Centauri anyway. There's a companion star named Alpha Centauri, and that you can actually see in the southern hemisphere. Anyhow, that's the nearest star to the Sun, and that is about a little more than 4 light years away. All right, so one thing that we've learned over the last 400 years or so is that you go back to the time of the Greeks, of course, a little bit, obviously before that, more than 2,000 years ago, and the Earth. There's a nice picture of our wonderful planet. Was really the center of the universe. It's called, in fact, that's called the geocentric model. Copernicus, as we're going to talk about it in a little bit, it really turned that idea on it over, and said that no, really the Sun, our star, turned out to be the center of the universe. And of course, in the beginnings of the 20th century, we found out that even that was wrong. That our Sun doesn't even occupy the center of our own galaxy, and our galaxy turns out to be one of hundreds of billions of other galaxies, and so so our place in the universe is nothing special, as it says here. Of course, we live on a very special planet, a planet that can sustain life and advanced forms of life, not just microbial life. Of course, our planet is the only planet that we've seen any evidence of life on. That doesn't stop us, of course. Even in our own solar system, there might be places that have life. in particular some of the moons of the outer planets, and we'll talk more about that as time goes on. All right, so the universe, what is it? So it is, as it says here, literally everything, all space, all time, all matter and energy. And today people talk about multiverses. That's not a very, for me personally, that I don't really like that term. There are some theories that predict there might be, an infinite number of universes. But the problem with that is going back to this idea of the scientific method, you have to be able to prove something with an experiment one way or the other. And there's literally no evidence whatsoever of multiverses, even though there's certain theories where the mathematics predicts that it should be there. All right, so getting back to our Earth, the Earth, of course, is roughly the diameter of the Earth is about 1,500 kilometers. Just to let you know, that's about 8,000 miles from one side to the other. Certainly not the biggest planet even in our solar system, but again, it is our world. All right, so there's a nice example right here. So of course we are the third planet from our star. We're going to go in much more detail about that. In fact, we'll go planet by planet as the semester rolls on. So as I mentioned before, we are one star. The sun is one particular star in a galaxy of stars, and that's actually kind of what this picture right here is. A nice picture of what our galaxy looks like. We live in a spiral galaxy, and we're nowhere near the center. And in fact, talking about light years, we're more than 26,000 light years from the center of our own galaxy. And our galaxy from one edge to the other, so like the diameter of the galaxy, if you will, is about 100,000 light years, roughly. All right, and so we live in a group of galaxies, a small group of galaxies, us and, for example, the Andromeda galaxy, so if this is us, let's say, and that's the Andromeda galaxy, the only other large spiral galaxy in our little local group, as it's called. The distance between us and Andromeda is about 2.5 million light years. All right, so that's just our local group. It's about anywhere from about a couple of dozen galaxies. Most of them pretty small. Just us and Andromeda are the large ones. And there's mostly what are called dwarf galaxies, really tiny little elliptical galaxies. Anyhow, that's our local group is part of what's called a supercluster, and a very large cluster of galaxies. Our supercluster actually has a name. It's called the Virgo supercluster, and it goes. It's much more than that. The Virgo cluster is just one member of many clusters of galaxies throughout the universe. All right, so let's going back to our star. Our star is really what generates the light, as it says. The heat and the light through a process called nuclear fusion. That is when two atoms, and all stars are mostly made of hydrogen, the simplest element in the universe, and gravity and pressure at the center of these of these stars causes what's called nuclear fusion. Basically, the hydrogen through a nuclear process that actually we understand pretty well. It joins together and becomes the next heaviest element called helium. And for a star like ours, for example, it spends most of its life, which we estimate to be a total of about 10 billion years, We're about halfway through that cycle, so we're about roughly 4.5 to 5 billion years into our sun's cycle. And so it's going to continue turning hydrogen into helium and sending heat and light out into our little corner of the universe. Here are some examples of planets within that orbit. Of course, the Sun, Mars, of course, the fourth planet from the Sun. Uranus. Uranus is actually very interesting. It's a gas giant. It's actually tilted about 90 degrees with respect to its orbit. Like it's like it's leaning on its side. We'll talk much more about that much later in the semester when we get to the outer planets, or also known as the gas giants. All right. The inner rocky worlds like Mars, occupy the inner part of the solar system. The gas giants occupy the outer part of the solar system. All right, and there's the rocky worlds are made up mostly of rock. The outer ones are gas and ice material as well. All right, I gotta watch the time here. All right, yeah, I still have some time. Of course, there's lots of moons. There's a nice picture of our moon, and yeah, we'll have a lot more to say about that. Moons are obviously, well, not obviously, but moons are objects that orbit planets. Our planet, of course, just has one natural satellite. There's many satellites around our planet now for lots of different things. Communication satellites, things like that. But we have one natural satellite. Mars, for example, has two. They're very small, Phobos and Deimos. Oh, I'm sorry. That's actually not. It kind of looks like our. Sorry about that. That's actually Ganymede, which is the largest moon in the solar system. It kind of does look like our moon. Anyhow, we'll notice you can see some craters and things like that. We'll talk much more about that. Within our solar system, there are little chunks of rock, tiny in the sense that they're generally much smaller than moons. These are average. Well, I don't know what the average is, but anywhere from maybe hundreds of miles. That would be the largest ones. The largest one is called Ceres. Anyhow, that's not important here. But there's some that are really tiny, maybe a couple of miles across, and a lot of them are very strangely shaped, and they're not big enough to have formed spheres because they don't have enough mass to do that. The mass is really what makes planets spherical, but a lot of them are potato-shaped. They will, they'll generally have craters, lots of craters on them. So it shows that there were lots of collisions in the early solar systems. And then, and most asteroids occupy the space between Mars and Jupiter. There's an area called the asteroid belt. The asteroid belt. That's not all of the asteroids, but most of them are found there. Excuse me. Of course, comets. A good description of a comet is basically a dirty snowball. The reason the comets have tails that we can see from the Earth is because they basically melt as they get closer and closer to the sun. And there's a nice example of that. All right, I'm going to actually pause this and then move on to the next one, the next video, that is.